Welcome everyone. Today we are going to see what are the requirements to program a design or to model a design using Verilog. Basics of Verilog. Now, what is the history of Verilog? In 1983, a company named Gateway Design Automation developed a language, hardware description language for its logic simulator. Later, that was bought by Cadence. Now, the current Cadence was earlier Gateway, as per records. Cadence made the language available to public, and later this language had to be standardized. So it was standardized by IEEE, and now it is Open Verilog International. Since it's Open Verilog International only, you are able to use it. Currently, it is maintained by Open Verilog International. That's why you are able to use the language freely. And the structure is based on C language. One thing that has to be noted over here, it is a case sensitive language. That means alphabets, capital letters will be treated as capital letters and small letters as small letters. Now, what are the various modeling styles or levels of description available in Verilog? The first level at the lowest end, base end, is the circuit level or the switch level model. Now in circuit level or switch levels, switch is the basic element. So the basic element in circuit level will be a switch. Now Verilog has inbuilt switches, basic switches will be available. So it will use MOS switches. So there are different types of MOS switches, PMOS, NMOS, RPMOS, RNMOS, and other switches which are available as constructs. So we can use that to model a program, model a design using switch level model. Okay. So one example of NOT gate is, I've taken the NOT gate simple inverter. In switch level model, this is how we are going to draw inverter. PMOS on the top and NMOS in the bottom. We have an PMOS transistor which is connected to VDD, NMOS transistor which is connected to ground. Now I give the input and Q will be the output. Generally what happens is PMOS will work when the input is 0. NMOS will work when the input is 1. Now suppose if I give A is equal to 0. If A is equal to 0, PMOS is on, NMOS will be off. NMOS is off. Now NMOS is off means I will not have a path over here. So what happens to the output? Output will be equal to VDD. So how is that? See, PMOS is on, NMOS will not be on, NMOS will be off. So this will not work. Only what will be working is this one. So when this is working, how will the output flow? The flow of the output will be like this. So what happens? What is the value over here? VDD. That's why VDD will be available at Q. Q will be equal to VDD. Similarly, when A is equal to 1, I told for A is equal to 0. Now when A is equal to 1, NMOS is on, PMOS will be off. Since PMOS is off, which is PMOS, the top transistor is the PMOS, the bottom is the NMOS. PMOS is off. So output will be equal to VSS. Output will be equal to VSS. So let us see that. So when A is equal to 1, this will be working and this will not work. So what happens to your output? Output will be equal to, Q will be equal to VSS. How is the flow? The flow is like this. So whatever is there in Q will flow down. It will flow down, so the output will be equal to 0. Output will be equal to 0. It will go like this. So the output is 0. Here it is. Here, it will be like this. So that is why it is VDD. This is how a simple NOT gate will work. So we'll see this in switch level modeling style later. The next example, okay, here in the same example, let me go to the code. Inverter, as you know, it has to only one input and one output. So one input is A, output is Q. Now this VDD and VSS are not inputs to the NOT gate. They are inputs to the design power supply lines. So supply 1, because this is will be having a voltage of 5 volts, which is equal to logic 1. Supply 1 will be VDD. Supply 0 will be ESS. Now, how do I write the gate? PMOS is an inbuilt construct. Gate number I've numbered it as P1. Now it is always output and input. In MOSFETs, what happens in MOSFETs is, NMOS you have three drain, gate and source. The terminals of the MOSFET, three terminals, drain, gate and source, will be having three terminals. Okay, so this terminal where Q is written, that is the drain. This terminal where VDD is there, that is the source, and this one will be your input, I mean gate. So drain, source and gate. Now when you write the construct, it is written in the format of drain, source and gate. So drain, source and gate. What is the drain for PMOS? Q. What is the source for PMOS? VDD. What is the gate for PMOS? A. Again NMOS. What is the drain for NMOS? Q. What is the source for NMOS? VSS. And what is the gate? A. So it follows the format of drain, source and gate, and it is written in the same format. Now let us go to the next modeling style. For the next modeling style onwards, we'll take an example of half adder. So as we know, half adder has two inputs A and B, two outputs, sum and carry. Sum is equal to A XOR B, carry is A and B, and this is the truth table for half adder. Now the second modeling style, what we are doing is gate level or structural modeling style, structural model. Now gate level modeling style uses inbuilt constructs known as primitives. So primitives are already available for gate level modeling style. We have a ready primitives. Now each primitive will be defined in terms of input and outputs. Always the output is first and then you have the inputs in inbuilt primitives. These primitives can be used to build larger designs. Gate level modeling style, you can assume it to be something on which something like a PCB design, building a PCB design. Now when you build a PCB, what will you use? You're going to use ICs, which are gates, and then build the design. Another thing is hierarchical circuits can be used to build, can be used using this type of modeling style. Suppose, say an example, building a full adder using two half adders. Full adder will be the top level module, half adders will be your sub module. So that is hierarchical design. So module half adder, sum comma carry, A comma B, input AB, output SC, XOR G1. There is no equal to, maybe it is written by mistake, you can ignore this equal to G1, sum comma A comma B, sum represents the output, A and B represents the input of the XOR gate. So take the XOR gate, what are the inputs and outputs? You are instantiating over here. Then it is the end module. So the next modeling style what we have is the data flow model. Data flow is the next higher level above your gate level. Now in data flow model, we are going to perform operations on signals and variables. Whatever are the operations available on signals and variables, we can use it over here. And the data flow model, see the modeling style will be concurrent in nature. All the expressions will be evaluated at the same time. Now data flow model, signals and signals are assigned through data equations. All the data equations, you can use it to assign the signal as shown over here. For our modeling style, for our design, if you're building a simple logic design, you can implement the Boolean expressions in data flow model. So modeling style S, A, B, C, this will not change, input will not change, output, because it's the same design, half adder. Now what is the expression for sum? Sum is equal to A XOR B. Assign, sum is equal to A XOR B. So we are going to use assignments. Assign, carry is equal to A and B. Now this symbol XOR and are logical operators. So we'll see what are the different logical operators in the next sessions, coming sessions. Next modeling style is the behavioral level. Now behavioral level constitutes the highest level of description, because using behavioral level will tell you the system itself. It is nothing but a replica of systems, but you're explaining it in mathematical, in your more, what I can say, programming language. That's all. It is simple to write like a C program, and it is dense in function. The compactness and comprehensive nature of this design makes the development process fast and efficient. Mostly we use behavioral language in wherever we go, if we have to model a design based on our requirements, until and unless the logic is available for us. If the logic is available for us, then we can go for other modeling styles. The behavioral model S comma C comma A comma B, input output. In behavioral model, compulsorily all output should be declared as registers. Now once I put a semicolon, it means that that particular line is completed. So 3 lines are over here, 1, 2 and 3. I've written it in a single line because of space duration, but these represent single lines. Always at A comma B. In behavioral model, functional verification is, first you have to write initial, then you have to write always. Now when we are writing this program, we need not initialize anything. Sometimes in sequential circuits, you may have to initialize your outputs to 0. So for such designs, you can use initial, but for this we don't require an initial, so we have not used an initial. Next, it is always at the inputs, put the brackets A comma B. You can write all the inputs to avoid confusion, but this list is, which is known as a sensitivity list, includes only those inputs for which the code is changing, for which there will be variations in the output. So sensitivity list, it will include the input for which there is a changes in the output. So you can also write always at star also. So if I write always add star, everything will be included. You need not worry. It will consider all the changes. Begin if A is equal to 0. So this is written for the truth table, dense in function. So we are writing for all the combinations of the design. So to make this more comprehensive in nature. So if A is equal to 0 and B is equal to 0, which is the first condition in the truth table, begin. Sum is 0, carry is 0, end. When you use multiple statements, you require a begin and end. If it is a single statement, we don't require begin and end. Else if the second condition is 0 and 1 in the truth table, begin, sum is 1, carry is 0 according to the truth table, end. Else if the third one. Else begin, sum is 0, carry is 0. For the last condition, you did not write else. If A is equal to 1, 1. It will consider if you write else begin. End, this end is for this begin. One more end to end your always begin, and then finally you have your end model. Next one is mixed modeling style. You need not model a design using only behavioral, only structural, only data flow. You can use a combination of all those as per your requirements and model your design. So here I have built one half-adder design using data flow as well as structural. Assign S is equal to A XOR B represent the data flow, and given, remove this equal to C comma A comma B represents the structural modeling style. Now this is a general format of the module. Since we have seen all the 5 modeling style, we should be able to give the general design. So module begins with the keyword module, module name, outputs, outs and inputs. This is how we are going to follow. Now what are these signals over here? These represents the ports in the Verilog. So what are the different ports we have in Verilog? The different ports we have in Verilog are input ports, output ports and in-out ports. Now what is an input port? Input port is nothing but through which one gets entry into the Verilog. Then I have output port through which one gets exit out of the design. And in-out ports, some signals or some ports which can act both as input as well as output. So this is how your module looks like. And here you have the complete design description or the code you can do. Now module will also comprise of other elements which are known as lexical tokens. So what are the different lexical tokens available in Verilog? White spaces, comments, operators, numbers, strings, identifiers and keywords. There are 7 lexical tokens which are available in Verilog. Now apart from writing the main module, we also write a simulation module or the test bench to test the working of the design. So when you write the test bench, what is the syntax? Module test. So this will define the declaration of the module. This represents the module name, semicolon. Here we don't have inputs and outputs. Then all inputs should be declared as registers here. All outputs of your design should be declared as wires. Then you have to instantiate the module. Write on all the test fixtures. Then you're going to give the end module. This is the syntax of a simulation module. Now, what are the things that is noted or which is important when you're modeling? Each module can be defined only once. You cannot define a module inside a module. Modules have to be defined independently. You cannot define, it has to be defined independently. Module can be instantiated any number of times. You can call your main module in your sub module in your main module any number of times, but the module name of the main module should be same. Example, full adder using half adder. In full adder using half adder, I use 2 half adders. So when I call the half adder, I should call the half adder, call instantiate half adder in full adder. Half adder, if it is the module name of half adder is HA, I should call it as HA gate 1, write the inputs. HA gate 2, write the inputs. So this design we have already seen during in arithmetic circuits. Now what are keywords? We'll discuss the lexical tokens. So the keywords are something which define the language construct, which is used by the language, which we cannot use as an identifier. A keyword signifies an output activity to be carried out, initiated or terminated. So that's what a program can use a keyword for what purpose it is designed and not for any other purpose. Now keywords, all keywords in Verilog. Verilog is case sensitive. All keywords in Verilog are to be in small letters. You have to write all the keywords in Verilog using small letters. This is case sensitive. Next, what is the font of Verilog modeling style? The font used in Verilog modeling style is Courier. So here when I wrote the code, you can see the font over here. It is of different font. This is different, this is different. This font is Courier. So Verilog uses Courier as the font. See, some examples of your keywords are module, end module, begin, end, if, while, all these things. Next is identifier. So anything which requires to be identified, a signal or a variable or a statement, you have to use a name tag. So those name tags are known as identifiers. Generally what we do, we use identifiers which are closely related to the design for our understanding. That's why when we designed half adder, I use the module name as HA, because it is useful for us to understand half adder. I can not use the name as the design, so I cannot write ECE because it will be difficult to identify which code it is. Now, what are the restrictions in defining or in assigning identifier names? See what happens. I can use all capital letters and small letters as identifiers. My identifier can start with underscore. Capital letters, small letters, I can use one. I can use all special cases also for identifiers. But what is not allowed in an identifier? This name with comma is not allowed. Dollar name is not allowed. You can also write comma name, that also will not be allowed. Dollar name is not allowed. One underscore name is not allowed. That's why when we did one example, if you had observed in decoder, I was trying to write the module name as 2_4 decoder. It did not take. So I wrote it as DEC24. So that is because an identifier cannot start with a number. It cannot start with an ampersand. It cannot have Boolean expressions as identifier names. This is one method of representing an identifier. There is another method to represent identifiers, that is using alternate format or escaped identifiers. Now what happens in escaped identifiers? Escaped identifiers always have this first backslash. So what happens when you use a backslash? So I can write backslash. Okay, this one. Let me take the last example. Backslash ABC. So this will be an identifier. So suppose this is the what I'm using for module name. Backslash ABC. It is also equivalent to write the module name as, say for example, module name I'm writing backslash ABC. This is also equivalent to write the module name as module ABC. Both mean the same thing. So this first character will not be considered. So this is how you're going to write identifiers. Ampersand logic, ABC. You can use this first forward backslash, which will not be considered as the identifier. So this is, we generally avoid this and we use the previous style. This we use sometimes in CAD tools. So the next one is white space characters. What are the different white space characters? Blanks, tabs, new lines, and form feed. 4 white space characters Verilog has. So if I write this forward a backslash and B, it represents a blank. If I write like this, it represents a tab. If I write like this, it represents a new line. And form feed, page breaking, going to the top of next page. Next, comments. Comments in Verilog are of 2 types. One is a single line comment, the other one is a multiple line comment. Now comments, it is a good practice to use comments as and when liberally, so that you can understand what do you mean by that particular line in the code snippet. So Verilog line, double line, if you write this /2 time, it represents a single line comment. So I've written module D flip-flop, Q DP clock, I've written like this. This means this is the design description of D flip-flop. In the next 2 line, I've written 2 more comments. But if this comment, if the first line comment is extending to more than 1 line, I can follow multiple line comments. So multi-line comments, it will have /*, write all the comments, again star and /, it will close. Whatever is written between these 2, this represents the multi-line comment. Next is numbers. There are different notations to use numbers in Verilog. So this is a very important concept. Next it is, numbers will be of 2 types, integers and decimals. Now, real numbers in Verilog can be specified in decimal or scientific notation. Suppose if I take the number as minus a dot b. So the decimal notation, when you're representing in Verilog, you can write the number as minus a dot b, which represents that this is a negative number. A is the integer point and b represents the decimal value. Here a dot b means you should write number, not a dot b. I've written it as a dot b as an example. It can be minus 2.3, minus 4.8, something like that. Now what about scientific notation to represent numbers with decimal notation? Now I can represent a number in this format, 4.3 E2. So 4.3 is the character and exponent to the power of mantissa. Okay, sorry. 4.3 is the mantissa and this is the exponent. 4.3 when it is the mantissa and exponent 2, which it means it is 4.3 into 10 to the power of 2. What is 4.3 into 10 to the power of 2? It is equal to 430. So this way also we can write the numbers. This is decimal. But integer number format. Integer number format, you can represent signed or unsigned numbers directly like this or like this. Okay, fine. To like this you can represent, but b, if I write variables b, a, all these things, it is not permissible because we are representing an integer number. Generally this will be for decimal numbers, and each number in Verilog will have 32 bits wide. If I write, even if I write a number 2, if I'm writing a number 2, the bit duration will be 32 bits. So 2, if I write 2, the binary will be 0000, 32 bits. So I calculate 32 characters. The last one will be 10, which is also equivalent to 2 in decimal. So this is what it means. Each number is 32 bits wide. Any number will be default assigned to 32 bit width. What is the next type of number format? Now this is the alternate form which we are going to follow. Here we have examples, elaborate notation for number system. How numbers can be represented: binary numbers, octal numbers, decimal numbers and hexadecimal numbers can be represented in Verilog. Now this is the alternate form what we are following. Hyphen 8 tick H F4. Now the first one represents the sign. The first field represents the sign and this bit is optional. Second bit represents the number of bits present in a decimal, in a binary format. Number of bits that is represented in binary format. Next bit represents the hexa. Dot tick represents which format you are representing. H represents hexadecimal, D represents decimal, B represents binary and O represents octal. F4 represents your number. Now 8 tick H F4 represents, F4 is 8 bit in size and it is a hexadecimal number. For octal numbers, for octal numbers, this is from 0 to 7. For decimal, it is 0 to F. For hexadecimal, it is 0 to F. For decimal, it is 0 to 9. And for binary, it can be 0, 1. And for all the other combinations, X, Z can also be used. For all the combinations, X, Z also can be used. Now here I am representing some numbers. 3, 3. Tick D 3, 3. Whether I write 3, 3 or write tick D 3, 3, both represents decimal numbers only. And it will be interpreted as 32-bit size. So I have represented this number in 32-bit size. So you can see the number size is 32-bit from here to here. This is equal to 32. Next is 9 tick D439, which represents, I'm representing, which tells us that I'm representing a decimal number 439, but 439 is represented as 9 bits. So it is represented using 9 bits. Next, I'll show this notation. 9 tick B1 underscore 1011 underscore 1x01. What does this mean? This underscore can be ignored. This underscore can be ignored. It is just like if I take an example of a 2:4 decoder with enable signal. If I take an decoder with enable, so let me take enable as one input and x1 down to 0, 2:4 decoder. Now what happens when I take the input, when I write the test bench, when I write the test bench for this signal, what happens, I will write it as enable comma x, and this can be written as 3 tick it will be. So 3 tick B. Now what is the value of enable? Active high enable, if I write, it will be 1. I can write an underscore to differentiate the space between enable and x, then I can write x. But together it will be taken as a 3-bit signal only. So that is why we have this underscore over here. This is also equivalent to whatever I've written over here, concatenation, enable comma x. It is a concatenated signal what I'm representing. This is also equal to 3 tick B100. So I concatenated, this is a concatenation what I showed over here. Both represents the same values. Now 9 tick 013 represents an octal number which is represented as 9 bits. 8 tick HA5 represents an hexadecimal number which is represented as 8 bit. So all these are similar examples. Now if you come to the next one. Next one is string. A string is a sequence of characters which can be enclosed within double quotes. So Verilog treats this sequence as ASCII characters. It will treat a string as a set of ASCII characters. Example, if I put anything within double quotes, it will be considered as string. That's why when we were writing sample programs, I wrote $monitor, I wrote $time, and what did I write? Next I wrote quote. So whatever I write in quotes will be considered as string. That's why that was printed in the console window. So that is equal to string. Next is after string we have operators. And when we come to Verilog operators, we have 3 types of operators. Unary operator which operates on a single operand, binary operator which operates on 2 operands, and ternary operator which operates on 3 operands. Now what is an operator and operand? If I write A is equal to B plus C, B is an operand, C is an operand, and the plus over here represents the operator. So this, if I have 2 variables, B plus C. So plus is operating on B and C, 2 variables, so that will be a binary operator. If it operates only on a single variable, then it will be a unary operator. For example, y is equal to naught of A. So here this not becomes a unary operator because it is operating only on one variable A. Okay. So unary operators do an operation on a single operand and assign the result to a specified net. Net is nothing but a wire in Verilog. We'll see net in the data types. So in operators, unary operators, I have logical negation, bitwise negation, reduction and, reduction NAND, reduction OR, NOR, XOR, XNOR. So these are operators. For logical negation, I can use this. Bitwise negation, this one. reduction and, or, nor, XOR and XNOR. Next is binary operators. In binary operators, the first one is the arithmetic operator. So multiplication, division, modulus, addition and subtraction. For example, 15 mod 5, the result will be 0. Okay, so similar examples which is given. I can use modulus for a negative number as shown in the table. Minus 4 mod 3 I can use, which will be equal to minus 1. But I cannot use 4 mod of minus 3. That option is not available in Verilog. So this operation is not available in Verilog. Next binary operator is a logical operator. First one was the arithmetic operators. In binary operator, first one is arithmetic. The second one is logical. In logical, I have binary logical operator. What is binary logical operator? These are logical operators involving two operands. In that I have and or. Then what happens in binary logical operator? The result of the operation in binary logical operator, the result of an operation is single bit. So it will either be true or it will be equal to false. Next logical operator is bitwise operator. Bitwise operator performs bit by bit operation. So here I have and, or, XOR and XNOR. The result of a bitwise operator will be 0, 1 or X. For this it will be single bit. So either true or false. Again, the next logical, see, this is the truth table of bitwise logical operator. Whatever digital systems we are doing and or XOR in half adder and all we use, they are all bitwise operators what we have used. Now, when you write a truth table for AND gate, what are the combinations you'll get? A and B is the input, Y will be the output, right? 0, 0. For AND gate, I'm writing 0, 0, 0, and will be 0. Again, 0, 0, 1 is 0, 1, 0 will be equal to 0, and 1, 1 will be equal to 1. This is the truth table for AND gate, right? But is this the same in Verilog? In Verilog, it is not same, because I told Verilog will take 4 values, 0, 1, X and Z. So it will take 4 values. Here I have shown a truth table which is taking 3 values, 0, 1 and X. Now when you perform an AND gate, 0 and 0 will be 0, 0 and 1 will be 0, 0 and X. X can be 0, X can be 1. So when it is 0 and 0, it is 0. 0 and 1 will also be 0. So 0 and X is 0. Similarly, 1 and 0 will be 0. So there's a mistake over here. 1 and 0 should be a 0. 1 and 1 should be a 1. This will be a 1 over here, truth table. Then 1 and X. What will be 1 and X? 1 and 1 is 1. 1 and 0 is 0. So 1 and X will be equal to X. See, I'll repeat it. When I take 1 X, X can take the value. It is equivalent to 1, 0. It is also equivalent to 1, 1. This X is 0 and 1. When it is 1 and 0, output will be 0. When it is 1 and 1, output is 1. So 0 and 1 represents nothing but it is X. So 1 and X will be equal to X. So similarly, we have truth table for AND, OR, XOR, XNOR and X negation. You can analyze this truth table. Next is relational operator. Now relational operator treats both the operands as binary numbers and it will compare them. The result is 1 is true. If it is true, then the result is 1. If it is false, then the result is a 0. So if it is greater than, it will give a result as true. If it is less than, it will give a result. This is less than, greater than symbol, less than symbol, greater than equal to, less than equal to. 4 symbols. Equality operator. Now if you see the equality operator, we used single equal to. Where did we use single equal to? Assign x is equal to a and b. For example, I'm showing assign x is equal to a and b. Here we used a single equal to. So single equal to is used as assignment operator in Verilog because it is used in assignment. What about this double equal to? I have a double equal to over here. So what about this double equal to? Now if two operands are equal by bit, the result is 1. Else the result is a 0. Double equal to is used for, say, I can say comparison. If x is equal to a. So when you're comparing two statements, you can use a double equal to. Result will be 0, 1 and x. This is negation equal to. It means it is a not. Then triple equal to. Now the only difference between double equal to and triple equal to is double equal to will give you a result of 0, 1 and x. But triple equal to only will give you the result of 0 and 1. Then this is negation of double equal to. So this is nothing but equality operators available in Verilog. But in Verilog, if you can see, I can use an equal to, which is an assignment operator. I can use a double equal to, which is used for comparing. So if two operands are equal, then the result will be 1 or 0. Or there's another condition for x. In Verilog, I can use one more operator, triple equal to. So what does triple equal to do? Again, triple equal to will match on a bit by bit basis, but the result can be only 1 or 0. It cannot have a x. So single equal to, double equal to, triple equal to, all can be used in Verilog as per our requirement. Next is shift operators. Only two shift operators are there, right shift and left shift. If the arrow mark is towards the right, so this is the operand over here. If the arrow mark is towards the right, it is shifted right. If the arrow mark, the point is towards the left, it will be shifted left. Now shifting will be done irrespective of the binary number being 0, 1, x or z. So if I take a number a which is equal to 0, 0, 1, 1, and if I shift it, a right shift 1, if I give, a will be right shifted 1. So what will happen to the right shift? If it is right shifted, means this bit will be lost. So what will be the solution? The solution will be 0, 0, 1. But what happens to the MSB? What will be the MSB over here? That is our question. What do we have as the MSB? So what will we be having as the MSB? Now, the bits that are shifted are lost. So this bit will be shifted right shift. So it is lost. So right shift. Now the vacated positions created as a result of shifting are filled with zeros. So this position is vacant. It will be by default filled with 0. If the right operand is a x or z, the result will have an x value. So what happens? Suppose if I have 0, 0, 1, x, this is the right operand is x, then the result will be equal to x 0, 0, 1. It will not be a 0, 0, 0, 1. This MSB is filled with x. Okay, similarly, even for the left operator also similar things will happen. So the next operator what we have is a ternary operator. Now ternary operator operates on 3 variables. So we can see I have the first variable over here w, second variable x, and the third variable is z. I have 2 operators over here, question mark and equal to. Now how does this ternary operator work? What will happen? This y will be equal to either X or Z. So how it will be evaluated? Y will be equal to W, or we can say W will be assigned the value of X. If W is equal to 1, it will be assigned the value of X, else it will be assigned the value of Z. So I'll write it in if statement. If W is equal to X, this is a pseudo code I'm writing, Y will be equal to W. If W is equal to 1, Y will be equal to W, else, I'll write it as if only, else if W is equal to 0, if W is equal to 1, Y is equal to W, else if W is equal to 0, then we can assume Y is equal to Z. That is what it means. So Y will be equal to, if W is equal to 1, it will be X, else it will be equal to Z. So this is known as a ternary operator in Verilog. So the next thing what we are going to see is logic values. We have seen all the lexical tokens. We have seen all the lexical tokens, 7 lexical tokens. So logic values. 4 logic values are available in Verilog. 1 significance the logic high, 0 significance logic 0. X represents an unknown or uninitialized value. So just we keep a note of this uninitialized value. X also represents an uninitialized value. We'll be checking this uninitialized when we encounter that. I'll tell you what is an uninitialized value. Z represents a high impedance state. High impedance state is possible when we have floating. High impedance state is possible when we have a floating line or a tri-stated line. Next, what are the strengths available in Verilog? So there are power supplies or signal strength. What can be the signal strength that is available to a line, to a wire, or to a net in Verilog? So when you take up of strengths available in Verilog, there are 8 strengths available in Verilog. Supply drive, we have supply drive, strong drive, pull drive, large capacitor, weak drive, medium capacitor, small capacitor, high impedance. Now, in a strength, I can have a logic 0 as well as a logic 1. If it is supply drive, the logic 1 is represented by supply 1 and logic 0 is represented by supply 0. Again, in Verilog, supply has the highest strength. Then comes strong. Then comes pull drive. High impedance will be having the lowest strength, which means if a wire or a net is driven by 2 signals with 2 different strengths, the one with the highest strength will prevail. Say, suppose I have a signal, I have a wire X. This X is having 2 inputs. One input is supply, the other input say weak or large I will take. Large 0 and supply 0. Okay, I'll take it as, I'll just for difference, I'll take large 1. See, I have X. X is driven by supply 0 and large 1. When you see this, supply is having highest value. Actually, X should be equal to 1 because 1 is higher. But according to strength 0, supply is higher value. So even if it is a low supply 0, the output will be equal to 0 because supply has the highest strength in Verilog compared to large. So that will be useful when you are using fan in and fan out signals, multiple signals driving a line. Next is data types. In data types, the first one is a net. A net is nothing but a connection from one circuit unit to another. Like you can assume by connecting wire in a breadboard. So net can be of two types. One is wire, one is string. Wire represents a simple wire for interconnection. Try will represent a signal line or a wire. Variable. Anything that is declared through the keyword register and stores the value of 0, 1, X or Z is a variable. Now, the next one is scalars and vectors. Anything which we represent as single bit. A variable represented as single bit is a scalar. A variable represented as cluster is a vector. So wire 3 down to 0, A represents A is a vector which is 4 bit in size. Why can't you represent from minus down 2 down to 2? You can represent. Minus 2 down to 2 represents D is a signal, D is a register value, register signal, which can have, it is 5 bit vector, which is of the size 5 bits. D of minus 2, D of minus 1, D of 0, D of 1 and D of 2. Next is parameter. Now parameters are similar to global constants what you use in C. Sometimes the variables have to be globally declared because you cannot keep on editing in the program. Such cases you can declare the variable as parameter. Suppose if I take an example for ripple carry adder. Now 4-bit ripple carry adder, what I will do, I will declare it as input 3 down to 0. If I want to change this ripple carry adder to n bit, 3 down to 0, A comma B, ripple carry adder. Okay, if I want to change it to n bit, now I should keep on changing this to n everywhere. So what I'll do, instead of keeping on changing this value, I will declare it as parameter n. Now if it is a 4-bit triple carry adder, I can use 3. If it is a 6-bit triple carry adder, I can use 5. I can use it. Automatically this will get updated. So that is where you're going to use parameter. Next is memory. This is used for declaring memory. Now this is an example I've given. Register 15 down to 0, memory 5, 11, 2 to 12. What does this? Register 15 down to 0, memory 5, 11 down to 0. What does this mean? This means there is a memory which has 512 memory location and each location is 15-bit wide. Like I can show, for example, this will be the 511th location. This will be 510th location. It will go up to 0th location. So 0, 1, 2, 3 up to 511. Totally will be having 512 location and each location is 16-bit size. So this is, you can store 16-bit data. So this will be the 15th bit, 14th bit, 13th bit, like that you can store up to 16 bits for each memory location. So it is like an array, two-dimensional array. So memory declares a two-dimensional array. So next we come to functional bifurcation with respect to behavioral model. So when we are writing programs using behavioral model, we have to follow this functional description is followed in other ways I can tell. Now what is that is being done in behavioral model? The functional description, two categories. First will involve functional description and interlink of functional units, and that is carried out through always. Second is during simulation, we have to set a starting point, initialization, steering the simulation flow and observing how the process variables are varying or how the process variables respond. In the, what I can say, how the output responds to the sensitivity list. So that is known as the initial. So functional bifurcation in Verilog is divided into two types. First is involving functional description. Second is using simulation. Functional description is done using always. Simulation is generally done using initial banner. So this is the general syntax I can say. Now if you can see the general syntax, so here type for how will you write, what is the syntax? So first you will write type of syntax at sensitivity list. Now type of block, if you are using always, in the type of block, if you are using always, it is always at the inputs for which this particular block, the declaration or the variables in this particular block, the assignments in this particular block respond. So all those inputs should be put under this sensitivity list. Always at sensitivity list. Now this at represents event control. We call this as event control. So what are the different types of event control? We'll see later. Then you're going to give begin. Name of the block is optional. If you want, you can write, else you can leave it. And here you're going to give all the assignment statements end. If you write initial, only initial over here, this add sensitivity list is not required for initial. So initial, begin, end, write all your statements within that. And next, you can use nesting of begin end blocks. Within one begin, you can write another begin. Within the other begin, you can write one more begin. So this end is for this begin, end with for this begin, end. So you can use nesting of begin and end statements. Now we're going to see Verilog constructs. The first construct, what we are going to see is the case statement, which we have already adopted in a 2:4 decoder. We can repeat it once again. So case statement, case, write the variables for which this statement is, this statement responds to. So case, expression, reference 1, this is related to reference 1, expression, reference 1, expression, reference 2, expression will get assigned to reference 3. The last one should be a default end case. So case, write the expressions of variables, then you have default end case. So this is the syntax for case. Next, if else, if else if we can use. So assignment, if you're using only an if statement, if condition, write the statements. Multiple statements are there, so you can use begin and end. If we are using an if else statement, if the condition begin end, else begin end. Now if you are using if else if statement means if begin end, else if begin end. We have to do this. Now we'll see what are blocking and non-blocking assignments. All assignments within an initial or always, so far they're all done with the equality operator. We have used an equal to sign for all the statements, assignments within the initial or always block. Now if you use an equal to sign within an always block, it is understood that the statements are executed sequentially, one after the other within an always block. Now such assignments, these steps block the execution of the corresponding steps. First line will be executed, then we go to the second line, then we go to the third line. It is not like first line, second line, third line, everything are not executed at the same time. Hence they are known as blocking assignments. Now if we have delays associated with the blocking assignment, when we add delays, the corresponding statements in the sequential execution flow will also get effective. For that reason, what we need is we'll use a facility called non-blocking assignment. Now non-blocking assignment means instead of using an equal to sign equality operator, we will use an less than or equal to operator. Anything with the symbol less than or equal to operator, those assignment statements become concurrent within an always or initial block. This is known as non-blocking. So let us see how this is working with an example. Now here I have given an example for non-blocking. I've considered A less than or equal to 2 tick B00, B less than or equal to 2 tick B01, and C11. What does this mean? All these statements, if it is put within an always block A, B, C, everything gets executed concurrently at the same time. So what happens? A will be equal to 0, 0, B will be equal to 0, 1, C is equal to 1, 1 at the particular time. Now if I put a delay, so I put a delay over here. What is the delay I've used? 2 and 1. So what happens? Again, there, if you can see, they're all blocking assignments. So I've used non-blocking. They're all non-blocking. Less than or equal to represents non-blocking. So what will happen? All the statements will be executed at the same time. A will be equal to 0, 0, 0. If A is executed at t time units, B will start its execution at t time units. So B will be equal to 0, 1. But there will be a delay with respect to the initial time. So it will be t plus 2. So here I have shown it as t1 plus 2. A will be assigned the value at t1. B will be assigned the value at t1 plus 2 because there is a delay of 2. And C will also start the execution simultaneously. It will be assigned the value 1, 1 at 1 nanoseconds. So what will happen if you see the result? If you see the result at 0 time unit, A will be equal to 0, 0. At 1 time unit, at 1 nanosecond, you'll not get B value, you'll get C value. C will be equal to 1, 1. And at 2 time units, you'll get the value B is equal to 0, 1, because it is all with respect to 0. 0 plus 2, 0 plus 1. This is known as non-blocking. Now, if you take a blocking statement, if you see the next example, these two are blocking and these two are non-blocking. So now how this works? Initially what happens? A will be assigned the value 0, 1, first step. In the next step, B will be assigned the value. A will be assigned the value 0, 0. B will be assigned the value 0, 1. Now I have non-blocking, which means both will be executed simultaneously. If both is executed simultaneously, what happens? A is taking the value of B. What is the value of B? B is 0, 1. So 0, 1 moves to A. Again, A is moved to B. Simultaneously, it is executed. So what is the value of A? A is 0, 0. So the new value of B will be 0, 0. After the block is executed, A will have the new value of B 0, 1. New value of B will be equal to 0, 0. This is how non-blocking will be working. Let me show another example for non-blocking. Okay, now non-blocking is okay for you. We'll see another example for blocking. Now I have A is 0, 0, B is 0, 1, A is equal to B, B is equal to A. What does that mean? First, all these are executed sequentially, one after the other. So in the first step, what will happen? In the first step, A will be executed. So A will be equal to 0, 0. In the second step, what will happen? B will be equal to 0, 1. In the third step, what will happen? A will be equal to B. A is equal to B. What is the current value of B? B is 0, 1. So A will be equal to 0, 1. Now in the fourth step, what happens? B is equal to A. B is equal to A. Now what is your A value? Current A value is 0, 1. So what happens? B will be equal to 0, 1. So this is respect to blocking statements.